All right, these are the video notes for section 2.5, substitution and elimination. And we're really continuing on with our discussion about solving systems of equations. So in 2.4, we did a little bit of it with graphically and also introduced the idea of substitution. Today we'll recap both of those methods and then go on to do our third method, elimination. When we're solving systems, the goal here is to find a solution which is typically a coordinate x comma y. So in other words, where do the two lines cross? But we also know from the previous section that they don't always cross. They could be parallel, which means you never get a common solution, so no solution at all. Or they could be the same exact line, a pair of them. So if you graph the same line on top of itself, you get infinitely many solutions, which means they share every single point in common. So let's start with a little bit of recap, review stuff, and then we'll move into the different methods and make sure we wrap it up with a couple examples of elimination. So one of the good skills to have when you're doing either graphing or substitution is to be able to solve one of your equations for one variable. And that's just a basic bunch of algebra manipulation. So if I want to solve for y, which means I want y equals, I need to move the x to the other side, divide through by -2, and now I've got to read as a y equals. Solving for y means doing that. But you don't have to solve for y, you can also solve for x. So in substitution problems, sometimes I just go for whatever the easiest equation is to work with, and sometimes that means I do solve it for x. So in this case I would get x by itself, again do my little bit of basic algebra, and now I've got an x equals equation. And then I would do is use that to sub into my other equation. And then, the variables could be something altogether different, but whatever you're asked to solve for that by doing your algebra. And now I've solved, so it reads n equals. Okay, so that's just a skill that is good to have when we're trying to manipulate one of the two equations so we can do substitution. And then some new terminology for you guys. We just want to hit a couple things here that are categories for how we classify the kind of lines we have. So we've talked about the types of solutions. You can have no solution, you can have one solution, you can have infinitely many. But when we have a system that has those types, then the system can be called inconsistent, consistent, and independent, or consistent and dependent. So I'll just take a second to highlight that. So it's kind of one more level or one more layer of how we would categorize the type of system we're dealing with and its solutions, how it connects to the solutions. So first thing, focus on the words from the previous lesson. No solution. One, which we said one unique solution, or infinitely many, and how they attach to the kind of graph you had. We know that no solution was parallel, so parallel lines don't cross, that's a no solution. And we say it's inconsistent, which means there's no consistency, no connection between the two in terms of solution. So there's no consistency going on. And another way of just saying that you've got parallel lines. When we have one solution, we know that they do intersect, so intersection means one solution. That means we do have consistency, which means a solution, but independent as in they're two different lines. So what's consistent is they're one coordinate, but outside of that, they're definitely independent. When we talk about infinitely many, we know that actually means the lines are identical. So there is some consistency, but in terms of solution, it's dependent because every coordinate on one is dependent on the other, or they're sharing all their coordinates. So we just want to attach the words now and kind of put it all together. So now we know we have a type of solution attached to parallel, and we have a way to categorize and talk about our lines. So here's what our solution, our type of solution, and here's how we talk about the two lines. And our type of solution and how we talk about the two lines. So that'll be added into the question. You'll be asked to fill in those as part of answering, like just kind of just a categorization sort of thing. And now we've got some new terminology that you need to get to know. All right, let's review our methods. So starting by graphing. When you guys are doing graphing, you can get them turned into y equals mx plus b, which is probably a good idea if you're graphing by hand. So there's a little bit of solving for y where that's useful, not just doing substitution. And then here a little bit of manipulation, get it solved for y and get my two lines. Now I can see that there's a common point, so that would be considered to be my solution. A single or one unique solution means it's consistent because we have a solution. It's consistent between the two of them, but it's independent, which means our two lines are actually different from each other. Also, don't forget about your friend Desmos, right? I can put these into Desmos and pop them up. In this case, with Desmos, it's kind of nice. I don't have to solve them for y equals mx plus b. And I can just kind of double check that what I drew or what I'm solving for, which is especially useful when you're doing substitution or elimination, is to have a graph as your backup. Okay. All right, let's go back to another example. let's do one substitution, and then we'll move into the elimination, which is our new method. So with substitution, the idea is I need to solve one equation for one variable. So here's the instance where I think it'd be better to solve for x. Just because it's when you have a coefficient of 1, that's typically the equation you want to solve for x, or solve for that particular variable. So I'm going to go ahead and just move the 3y to the other side. Then my substitution happens by me plugging that equation into the other. Make sure you go into the other equation when you do that. So we're going to go 2. I'm going to leave a parenthesis there because that's where the substitution is going to happen. And that equals -8. What I'm plugging in place of x is what I just figured out I would like to call x, which is 3y minus 6. Now comes the cleanup part of the problem, so we're going to go ahead and distribute. Get your terms combined, so my y terms would be 2y, subtract that 12 to the other side, -20, and y is equal to -10. Now, one thing to keep reminding yourself is that that's only half of a solution. Right now, you know this much. We still need the x, but what's kind of nice about doing this upfront step here is that gives me an expression that I can plug into, so I'm going to use that. So I would grab it as something I want to plug my equation, my y value into. So here we go. I'm going to go ahead and just use that equation real quick, plug it in. So I'm going to get 30 plus 6, or x is equal to 24. Now, there's a full solution. Now, the fact that I got one solution, which means consistent, but my lines are two different lines, independent. Okay, so just one more kind of layer again we can add on to the overall picture. Now, we're going to switch over to the process of elimination, but I'm going to use the same problem, and we'll look at it in Desmos here too in a second. I'll tell you what, I'll do that after we get to the second one. So we're going to use the same exact problem, but switch the method. And then we can kind of verify that we're getting the same solution here. So the process of elimination is definitely a little bit different. What you're basically trying to do is create a plus and minus of the same variable. And then once you've created that situation, you want to add them together, and then the solving will take place from there. So when I look at my pair of equations, I'm trying to decide which one I'd like to eliminate. Typically, if I see, again, this, that tells me I'll probably get rid of that variable because it'll be the easier one to change over. So what I'm going to do is I'm going to multiply this equation through by 2. And the goal, again, I'll show you what happens in a second, is to create plus and minus of the same variable, which I just accomplished by creating there was a -2x to begin, I created a positive 2x. And when I go to add these two equations together, the variables will drop out, the x's will drop out. Now, it's kind of up to you guys how much you want to reorganize and rewrite. You could just go right from here and say addition, but then just be clear which two things you're adding, which are these two. You could rewrite it, I suppose, sort of separately and put it on another spot on the page, but I think this is probably the least amount of writing. So the idea, again, is those become a 0. Add your, and when we add, by the way, we add down in columns by like terms. So this would be a positive 2y, and then I would get a -20. So if I divide by, then I'm going to get my -10. Now you notice that was the same value we had in the previous problem, doing it by substitution. And then what I'm going to do is I still only have half of a coordinate, which is still only half of a solution. So I've got to take one of the two original equations. It doesn't make much difference which one I use, but I'm going to grab the bottom one. Now again, I'm using the original. And then what I'm going to do is plug in that -10. So you can see I got, again, the same solution. So I got a solution, which means consistent, but my two lines are different lines, so it's independent. So what we're trying to do here basically is just show you between substitution and elimination, it doesn't make a difference which method you choose. It should produce exactly the same result. Now, as far as graphing goes, again, I'll check it out with you guys on Desmos, so let's get rid of those two. So here they are. And that solution actually is sitting kind of way out there because remember it was 24. But 24 -10. Okay. Again, Desmos I think is a great backup when you're solving a system algebraically where you don't actually have a graph to look at. But you can go see like, hey, does it match up? Did I get what I expected? All right, let's try a couple more with elimination and talk about some of the other things that can happen as you guys are doing these problems. So there are some, how am I getting some of the other types of solutions, like a no solution or infinitely many? How does that show up when I don't have a graph in front of me? I don't see a set of parallel lines. I don't see that the line is the same necessarily. Well, I'll show you how it shows up. When you do elimination, again, the idea is get rid of one of your variables. So let's say I decide to get rid of x again, and I multiply this one through by -1. What that's going to do is give me -x, -2y, and -8. And then again, remember, you're going to add down in columns. Well, look what happens here. X and -x, that's a 0. Positive -2y, that's a 0. And then I get -14. Well, here's what happens when both variables drop out and you get a false statement, because 0 does not equal -14. And you also lost both of your variables. Just think of it this way. False means no solution. And no solution means these lines must have been parallel. And parallel lines would be inconsistent. We don't have a choice here. They're just inconsistent, meaning no solution. So you might not notice that, by looking at the equations for sure. But again, I could go to Desmos to give myself a little quick visual and see that I have a set of parallel lines. But if I'm not looking at a graph, then the way to determine that is based on what happened with my solving. And the key there is that you got both variables dropped out and you got a false statement, and false translates to no solution. Okay, let's check out how the infinitely many would look. So again, you don't really notice it first, you just kind of start your normal work. Let's say this time we're going to get rid of y, so I'm going to multiply through by -3. And the reason I'm choosing -3 is because that would create a plus and minus. So I'll do that multiplication, -6x, -3y, -18. Remember, we add down in columns. So plus and minus 6x, 0, plus and minus 3y, 0, plus and minus 18, 0. 0 equals 0. Well, that's actually a true statement. So here's how you determine that it's the same equation or infinitely many solutions. Both variables dropped out and you got a true. So true means we have a solution, but because both variables drop out, that means we have the same equation. So infinitely many, which is going to be consistent. We have solutions, but they're dependent because, again, they don't have a single solution. Now, graphically, check those two out. And you notice, watch, now there's the first one graph. Now what happens is it graphs right on top of it. If I was trying to find points of intersection, it's everywhere, right? There's all these points so all those points are in common, infinitely many. Okay. So that's how I know. Now, one last problem we'll do is like one more that has an actual coordinate solution, but we do need to know these two for sure because they do happen, and when this happens, we got to be clear, like, not that I did, so you don't think you did it wrong, but you know what this is telling you without having to see the graph. Okay, let's get one more round in. So elimination again, pick your variable, which one you want to get rid of. I don't think it really makes much difference. But if I have a lone y, I'm going to do that. Actually, let's do it as though we're going to get rid of x. So let's talk about that. Let's say you just choose to get rid of x. Well, then here's what I'm going to do. So it may be that I have to multiply both equations by something. What that's going to create is a plus 6x and a minus 6x. Now, in this case, because I'm multiplying both equations by something, I think it's best if I rewrite them. And then down here we have -6x, so there's that plus minus situation I was trying to create. And then again, I add down in columns. So y is equal to +1. So now what again I have is a partial coordinate. And then I would take that value and plug it back into either one of the original two equations. Again, it doesn't make any difference which one you're going to go into, but I think I'm going to use the bottom one just because it seems like that's a little bit easier. So in that spot, I'm going to put a 1. Okay, so there we go. I'm getting a solution. Now, the fact that I got a solution means it's consistent. The fact that they were different lines means it's independent. And then I could also go check it out on Desmos and see how and there we go. There's my two equations. And check out my intersection point 3,1. So Desmos to me is a backup. Don't try to rely on it solely to the problem because, ultimately you're going to have to be able to do this work. But that's basically now comparing the three methods. We've got graphing, we've got substitution, we've got elimination. The goal being try to figure out what's a solution to a system of equations. And that'll do it for your 2.5 video notes.